Okay, welcome back. Let's take a look at number 26. And this is talking about fish length, okay? And it says, assume the length L in centimeters of a particular species of fish after T years is modeled by the following graph. So you have this function here where your y-axis is L, okay, and your x-axis is T, okay? And let's go ahead and put some labels on this. And this is length, okay, in centimeters, okay, and this is time in years, okay. So what we want you to do, you have this function L, okay, and it says what does dl dt represent and what happens to its derivative as t increases, okay. So if I were to calculate, dl dt, then you have to think of this as similar to like the change in L divided by the change in T, okay, the slope of that, to put some labels on it. And so what I want to do is I want to replace my L over here with centimeters. So change in centimeters divided by the change in hour or years, okay. So this is a function, or the derivative represents centimeters per year, okay? And so, it's the rate at which the centimeters change per year, okay? And so that's what we want, how we want to interpret this. This is part A, okay? The rate at which centimeters change per year. And so that's really what dl dt is, okay? So it's a rate of change, okay? And then it says what happens to this derivative as t increases. So let's graph dl dt in red. And what we see here is if we were to kind of take all these little slopes across this curve, you notice that the slopes get less steep. So your graph does something like this, okay? And so, as t increases, all right, and that question says, as t increases, what happens to our derivative as a result? And what happens to the rate at which the fish grow in centimeters per year? And so in part, in part of part A, we would say that the rate decreases as t increases, okay? So, some interesting things are happening here. And so, that's just what's going on, okay? And so let's take a look at part B. Part B says, what does the derivative tell you about how the species of fish grows? And what you can say in part B is that the fish grow faster early on, and then they don't grow as fast as t increases, okay, as the year goes on. So what we've done, and then it wants us to sketch the graph of L prime and L double prime. Well, this graph here in red is L prime, okay? And then we want to graph L double prime. So I'm going to take a look at these slopes here, and these slopes are negative, 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 but they're approaching 0, okay? So they're down here, and we would graph L double prime like this. This is L double prime. Okay, so let's go ahead and take a look at the next one. Okay, on the last question, number 32, this is a question about fuel economy. This is an interesting question and an interesting function. Let's say, suppose you own a fuel-efficient hybrid automobile with a monitor on the dashboard that displays the mileage and gas consumption. Okay, so you can look at this and it says you have the number of miles you can drive with G gallons of gas remaining in the tank on a particular stretch of highway, given by this function m of g, okay? And this is, you're given this function, this quartic function, but then you're restricted to know that you're only dealing with the first 4 gallons of gas, okay? So, that's where this statement here, gallons of gas between 0 and 4 gallons. So, let's label this graph first, okay? And let's give the x-axis, and I'm going to say gas in gallons, okay? And so let's look at the y-axis. The y-axis would be the number of miles you can drive. So the y-axis is the number of miles driven. Okay, number of miles driven. Dear. Okay. And the x-axis is really gallons of gas used. Okay, of gas used. Okay. So, it's important that we can label those axes. Okay, I'm going to label this G and label this M. Okay, and so we can graph and interpret this. So what we know is that, and it's kind of hard to see it, but I can kind of see it. I notice that this graph right here, the graph, the number of miles that you drive, tells you how at the rate at which you can consume miles per the gallon, okay? And so what I notice here is on the first, gallon or so, your efficiency isn't that great, okay? You're concave down, and then all of a sudden you get concave up again, and then all of a sudden you go concave down. So right in the middle is kind of the sweet spot where you're using, your car is performing very efficiently. Okay, as you use gas over this interval of time right here, then you start to, not use it as efficiently here. So, it says graph and interpret the mileage function. So, we've graphed it, and all I want to do in part A is say that the gas is most efficient, not with a P, efficient from, I'd say about 1.5 to 2.5 hours from from gallons, G equals 1.5 to G equals, say 2.5. Okay, not time. I'm thinking not the right thing here. So, okay, so that's per gallons. And that's, you're kind of just describing what's happening on A. Let's go ahead. I'm not going to do part B, but let's take a look at part C where it says graph and interpret the derivative of your mileage function. Okay, so at what rate is your miles per gallon the best? Okay, and so what you can see here is that the rate at which, so let's write this. Let's write in part B, dm dg, okay, is the rate at which the miles are driven depending on gallons used, okay? Which is kind of hard to interpret and kind of find the meaning of. This is kind of tricky, okay? And so what we know, if we look at this function here, okay, our derivative function, let me move this down a little bit. As we look at our derivative function, we notice that the rate at which, we're the miles per gallon is decreasing here. And then it seems to be increasing from like 1 to 3, okay? So when we're increasing our miles per gallon, we're going faster up here. So really, and let's write this in part B, the rate is decreasing from 0 to 1 gallons and from 3 to 4 gallons. Okay. We know that the rate is increasing from t equals 1 to t equals 3 gallons. Okay, so that's really what's happening here. And it's interesting. If you drive your car for a long time, you'll notice that there is a point at which depending on how much gallons of gas you have in the car, your car will perform differently. I noticed that in my car, if I'm on a road trip and I'm driving the first 100 miles, my tank holds like 300 gallons or 300. I can go like 300 miles on a tank, and I noticed that my, in between like 50 miles and like 150 miles is when I feel like I utilize my gas most efficiently. Okay, I can like watch the amount of gas in the tank, how it drops. It seems to drop fastest, after 150 gallons. When there's less gas in the tank, it seems to not perform as well. So, those are little things that you think of, and we can, model them mathematically. But this is kind of some interesting stuff. So I hope you learned something from this, and we'll see you in a few. So thanks. Bye.